just joined.
Oh, good.
Hello. Hello, everyone. I'm Hara from AIST Japan.
Okay, I'd
you
like
hear
to
me?
start. Yes, we can hear you.
Thank
So
you.
I would like to start today's session. I'm Jun Kawai from Kyoto, and today's speaker is Dr. Shiro Hara, and he is working on semiconductor processing or something. I'm not sure the details, but because of the semiconductor silicon processing, he is very familiar with contamination species to the silicon wafers and its concentration. How low concentration or how high concentration affect the function of the circuits. And so it's some kind of revival of TXRF. So total reflection was at first, maybe before 2000, it was used for the semiconductor industry. And now, because of Hara is proposing minimal fab system. So because of such kind of system, again, we have some possibility to use TXRF for contamination control. So maybe we will start, we must ask Hara to start your talk. So please.
Thank you for your introduction of mine. Anyway, first of all, I will thank all the organizers and participants in this presentation. Anyway, I thank the chance to present my work to you. Thank you. So let's start. Okay, I will upload my file. 1 minute. Okay, can you see my presentation material?
Yes, yes.
So
yes, we can see.
The presentation mode. Okay, and I will use laser pointer. Can you see my laser pointer? Okay. No.
Yes, yes, we can see.
Okay. Okay. Let's start. So today I will talk about two categories. The first one is minimal fab itself, and second one is contamination control in semiconductor fabrication and our work using a minimum fab, etc. So, anyway, first, minimum fab is a new concept of our AIST. So this is aiming to create a minimal semiconductor factory. So the word minimal here means to operate something consuming least resources, like least energy, least materials, least cost, but to fast operation, which includes sustainable business and industry, I believe. So I will introduce my co-workers and organization. This is me, and this is my co-workers in AIST National Lab. And we are developing a core technology of minimum fab. And also separated from AIST, I established a minimum fab promoting organization. So under the organization, we have established the Fab System Research Consortium, including many companies. I'm a representative. So using minimum fab promoting organization, we are selling tools or prototyping the devices, or we are selling devices, etc., etc. Devices, not the tools, etc. So these are our communities. There are many companies. Red-colored companies are big companies, and the black-colored ones are medium and small-sized companies. And almost all companies are Japanese companies, but recently, SVCS in Czech Republic, it's a kind of a LP, low pressure CBD maker, was participated in our community and developing ALD, atomic layer deposition tools now. So we are extending our community to many companies outside Japan, countries outside Japan. So let's go to the background of the minimum fab. As you know, the wafer size is enlarging like this, unbelievable. so our way, but there are many disadvantages of the making using large wafers. The first one is huge investment, as you know, and the second one is enormous waste, and third one is value of this in R&D, and the fourth is not suitable for low volume like IoT devices. So therefore, our way should take the opposite way of using 0.5 inch, very small wafer like this. So this is our minimum fab. There are many tools have been developed. Please note that these things are different processed tools, not the same one. So we want to individualize industry to a very small size. But I will explain the individualizing the big market. So for mega manufacturing system, there are many mountains and valleys from the research section to through industrial research section and a factory. And after factory, before market, there are big valley. But important thing is that the big market is individualized to many small markets. So therefore, we can retrieve one of the big market like this and reconstruct the small size of mountain valleys like this. There, since the height and the valleys are very small, we can apply our generated innovation or new findings to the industry very easily compared with the manufacturers. This is the minimal way. So to do that, I considered deeply how to promote this one. My conclusion was that the product should be research sample size. Do not use a huge wafer in the midway of your production. Your production iPhone does not have a large wafer. You always use a very small devices. So, but also research scientists also use a very small one. So please don't use the huge wafer in the midway. So the second one is the high quality control. This is very important because our yield of research, yield of our research world is very low. Since our work is a challenging one, but it is a very tidy and very not happy one anyway. So we should raise the yield of our experiment. To do that, I get rid of contamination from our research space using my invented localized clean technology. So anyway, minimal way is an ideal to solve the issues. So we met the very basic question: to what degree do we shrink the fab size? 1/1000, or 1/1000, or 1/100 or so? We don't know. But according to my huge amount of interviewing to the practical people in a semiconductor world, in a device fab, number of WIP means work in progress product types at the moment is 100 types at the moment. I mean that in a fab, there are many types of devices are fabricating at the same time. Unbelievable that the number of types it's 100 types at the same time. Unbelievable. So one type at a certain moment is an ideal fab, of course. Therefore, we make a fab 1/1000. We call this fab 1/1000 minimum fab. So we use a tiny wafer intentionally. So let's summarize the minimum fab. So in a mega fab, we use a wafer size of 12-inch, or actually 300 millimeter. So we shrink the wafer to the 1/1000, and the resultant wafer size is 0.5 inch. And as a result of shrinking the wafer size, the tool size is at the same time is shrinked to the size of 0.3 millimeter in the width. And in addition to this, we have developed a no clean room system using a localized clean system. As a result of these things, 1, 2, 3, the fab investment of $5 billion goes down to $50 million or $5 million, also very small. So to do that, there are many challenges for minimum fabs. First, we have to develop localized clean technology, and we have to reduce the R&D cost to develop minimum fab itself and devices. To do that, we standardizing everything except the processes. And we have to develop processes and devices, and we have to find low volume markets. But today, I will skip the section 4 today. So let's go to the local clean technology. So this is my very small wafer vehicle. It is called minimal shuttle. And inside the minimal shuttle, there is one wafer, very small one. And we land or set the minimal shuttle to the wafer loader. It is called PLUD. PLUD means a particle lock airtight docking system. And this PLUD is mounted to the midway of one tool. It is installed. So, and the wafer is transferred from tool to tool by hand or mechanically, automatically, like this. So this is our system. And I'll explain the cleanliness of the PLUD system. If you close the PLUD system, the particles goes down very quickly and within 20 seconds, we observe no particles at all. So it's less than super clean room. Our performance is very good. So, and this upper lines means office clean room, not clean room, but the office room clean level, and lower ones are ours. The difference is 5 order of magnitude or so. This is very good. We achieve super clean without clean room. Please notice that. And let's go to the standardizing. So we have to standardize everything. The first tools, the tool, the height is 1440 millimeter, and width is 294 millimeter. And the reference of using this kind of difficult formula is that the number is that we have to make a space between space with 6 millimeter between the two tools. So the periodicity of the tools is 300 millimeter. And also we standardize the wafer size, not the 12.7 inch, not inch, but millimeter. To 12.5 millimeter is our diameter. And this is a minimal shadow. It is standardizing, of course. The reason of the red color is to protect the UV light from outside to the wafer. So, of course, we standardizing the plot system. And also, we standardizing machine controllers using Windows 10 Embedded, etc., etc. So we use a very advanced EtherCAD system, etc. So, and also we use standardized user interface. User interface is unified for all the tools which are made by various makers. Area operations are also unified. Then you can learn about minimal fab very easily. And also we have to make a worldwide standard. So we have to make a defect standards for material handling, wafer, tool size, machine control and UI, and a factory system. And we have to make many inventions, of course. And so blunt image is also important from a copy system from unbelievable companies. So we have to design this kind of nice style. And also another important thing is that to make a logo for this machine, and we did production authorization to protect our minimal fab standard. And let's go to the actual processing technologies. So using our minimal fab system to make a transistor for 30 processes, it takes only 10 hours and 25 minutes, unbelievable. So, and after half a day, we can make a transistor because our fabrication time is very small, very quick, and the exhausting of the evacuating the chambers is very quick because we evacuate wafer loader within 15 seconds because the volume of the wafer loader is only 1 cc or 1 cubic centimeter. Okay, so it's very small. So evacuating is very quick. So we don't have to wait the evacuating. So anyway, as a result, R&D speed of minimal fab is 100 times than traditional prototyping fab. So one researcher can make a device by yourself, by himself or herself. And I will introduce a little bit about the processes and devices. For wafer cleaning, we found a very interesting phenomena like this. Please look at this. So since the wafer size is very small, there occurs a very strong surface tension. As a result, the liquid is dropped, but there's no pouring, no drop out from the wafer. And the height of the liquid is 4 millimeters, unbelievable. So after discovering this interesting phenomena, we only use this amount of liquid to clean up the wafer. So the chemical consumption is 2 milliliter per wafer, with ultra pure water of 10 milliliter per wafer. So minimum fab saves material resources, very small one, and is needed for resources. Now I will introduce plasma technology. So in the mega fab, plasma attacks the chamber wall because the wafer size is very small, very big. So that chamber size can't be extended like this. So the chamber wall is very near from the edge of the wafer. So the plasma attacks the chamber wall every time. So, but for minimum fab system, the wafer size is very small and the plasma size is very small, but the chamber size is 10 centimeters or so. So therefore, plasma don't attack the chamber wall, no reaction with the wall. So as a result, plasma works ideally in a minimum fab. Unbelievable, very simple one. So, and also reactive species are exhausted very quickly because we don't care about the reaction of wafer with the wall. And as a result, we can etch this get a very nice walls like this. Please look at this one. This is silicon etched surface, and the width is 1 micrometer and height is 10 micrometer. Unbelievably, you don't. I believe that you don't see this kind of unbelievable strong, straight line of etched surface of silicon. So minimum fab advances process technology. And let's go to the device applications. So we succeeded in making a cantilever in 1220, and year by year we are developing many devices, and nowadays we are developing integrated circuits, etc. These are our transistor structures. So this is the example of the IC, very small, not the most advanced one, but we can make very simple ICs so far. And this is a very interesting one. We can make this kind of a very unique device unifying CMOS and MEMS technologies. So I will skip the low volume market today. This is very interesting, but please, let's go to the another one. So anyway, summary for part 1. We have developed a minimum fab. Only one person can operate all the minimum fab tools by himself. We have developed CMOS IC and MEMS sensors. We have developed our RDL technology for 2D, 2.5D packaging and TSV technologies for 3D packaging. Sorry, I have skipped this part, this section today. And also, almost wafer process tools are commercialized, and minimum fab is used for prototyping devices now. And minimum fab is grading, aiming for production fabs. That's all about the part 1, as an introduction for minimum fab. And if you don't, if you have any questions, or I can go to the part 2 of contaminations. Professor Kawai and other people, do you have any questions?
Yeah, hello, this is Armin. Can you understand me?
Yeah.
Just a very simple question. Why did you go for 0.5-inch wafer size and not a 1 or 2 inch? For example, 2 inches very popular in R&D.
I think so. Good question. Thank you. So if you adapt to 1-inch wafer, the total cost of developing of the fab is 4 times, because the 1 inch is doubled of 0.5 in diameter, but the area is 4 times. In this case, total developing cost is 4 times. We can't collect this kind of huge money. This is one reason. And also, if you use a 1 inch wafer, we should adapt very large, huge, bigger tools whose width would be 6 centimeters. So it's too big for us. It's like smallest tools which are using in the world. This is too big for us. This is that was another reason. And the third reason is that we want to use the scanning technologies. So for scientific world, we are using scanning technologies for irradiation and detecting systems, as you know. But no one don't want to use for larger wafers because it takes time. So this is a big difference between the science world and technical world. We have to combine. We want to combine it. To do that, a bit smaller size is better. And there are many other reasons, but the main reasons are like this. Can you understand this?
Yes, thank you very much.
You're welcome. Do you have any questions? Any other questions? Okay, shall we go to the next part? Okay, wait a minute. Yes. Okay, I'll change my view graphs to the part 2. Can you see that?
Yes, we can see.
Okay, thank you. So I will talk about the particles and atoms. So there are 2 types of contamination. The first one is particle, and the size is like 0.1 micron or so, which is converted to the atom number of 1/10 to the 9th or so, a huge one. But the particle disconnect the device wiring, etc., of course. And second one is atom or molecule. The size is 0.1 nanometer or so, and it degrade or modify or break the transistor characteristics. So first, let's go to the particle. So first of all, we did a very interesting important experiment, very principal, very basic one, but it is important. So the question is, what amount of particles are generated from rubbing or collision? So there are 2 kinds of experiments. The first one is rubbing horizontally, and the second one is collide vertically. So as a result, how many particle is generated? Can you imagine that? So for rubbing horizontally, how many numbers of particles are generated? 10 particles or 100, 1,000? How do you think about it? And how about the collision vertically? No one don't care about that, but we did that. So the answer is unbelievable one. Unbelievable. So the answer is that 20,000 or 30,000 particles per one rubbing. But for collide vertically, only 1 particle or 0 was observed for one collision. Unbelievable. So this is a detailed graph, experiment graph. So I take a number of rubbing or collision horizontally, and the other vertical axis we takes I takes a cumulative number of particles on a wafer observed. So please look at the vertical collision. This is depicted by the blue lines. So for 10 number of rubbing, the resultant observed number of particles is 15 particles per 10 wafers. So 1.5 particles per wafer is the results, as I said. So unbelievable, very small. But for rubbing horizontally, there are many particles have occurred, and we observed many particles like this. So they're totally big difference, unbelievable. But we found that the vertical collision is okay, but horizontal rubbing should be prohibited. So it is suggestive to use O-ring. So if you use O-ring with rotating materials, that's not good. That's not good. But or you use O-ring with a collision vertically with a material, that's okay, no problem. So after finding this unbelievable result, I designed minimum fab using this kind of principle. So we exclude the motion of the rubbing inside minimum fab completely. As a result, minimum fab don't generate the particles inside the minimum fab. No one don't use this kind of things in the world. So, and another one is that this is a very interesting view graph, and the horizontal axis is the exposure time of a wafer to the air, and at horizontal at a vertical line axis is a particle number on a wafer exposed to the air. So. So this red line is a line for one particle adhered, okay? And also, for this, to observe one particle on a wafer, which has a size of 1 centimeter or so, it takes 10 seconds, okay? After 10 seconds, within the 10 seconds, you will find one particle on a wafer per 1 centimeter. And this is a range of typical minimal fab class. So minimal fab tools, number of particles over 0.1 micron on a wafer exposed to the air for 5 minutes. 5 minutes, usually 5 minutes to 10 minutes. It takes much time to observe one particle. So this is not, there are no problems for minimal fab. So 4 minutes also, no particle adhered on a wafer per centimeter, okay, per square centimeter. So we have known that for dry process or airborne particles, no problem. But let's go to the next one. Liquid process is very important for particles. So there is another experiment to dip the silicon wafer to a beaker to clean in a clean room or a non-clean room. It is a very interesting experiment that people can't do that because you have to control the cleanliness of the clean room, and after that you don't care about particle number on the wafer. It is very sophisticated experiment, but we can do that because we can use a minimal fab with technology of local clean technology. So The experiment is to clean the wafer using a liquid process like this, DI water, methanol, piranha solution, and rinse DHF, etc., and drying. And after that, after taking the wafer from the beaker, we insert the wafer to the minimal shadow and go we set the minimal shadow to the minimal fab wafer particle scanner and measured the particle measurement like this. And as a result, for the office clean room level room, there are many particles on the wafer were observed. But for a lightly cleaned room, the cleanliness is 2 order magnitude lower than the office is like this. So I mean that for wet cleaning process, many particles is invaded or inserted into the water or liquid, and liquid with many particles contaminates the wafer. So airborne particles adhere to a wafer in a wet process, not a dry process. So this is a story of a particle which has not been known in the semiconductor world, but we have known the basic phenomena for the particles. And let's go to the next one, atoms, molecules. So I have to explain first of all, the basic principle of the degradation of devices. So to do that, we have to explain the Schottky barrier height. So as you know, Schottky barrier height is formed after making contact with the metal and semiconductor. And there's a bending band gaps. As a result, the bending height is called Schottky barrier height. But for actual semiconductor, as you know, there are surface states like this in the band gap. So actually, the surface is bended, of course, but anyway, to make a contact between this, the Fermi difference between these two is neutralized by flowing the electrons to the other, and as a result, the semiconductor is bending like this, and the resultant surface state is called interface states. So since the amount of the interface is very large, it's like a huge water basket. So the surface, water surface is pinned to the interface state, for example. So as a result, is called Fermi level pinning. So as a result, Schottky barrier height it cannot be changed easily. So by changing work function of metals, I mean that if you change even if you change the metal or metal work function, the barrier height can't change very easily. It is called pinning. So the rate of the changing of the Schottky barrier height depending on the changing the work function is called S factor. So and the S factor is from 0 to 1. If the S factor is 1, it means no density of interface states. And if S is only it takes only 0 or near 0, there are many interface states. So and I will take this kind of graph between the density of interface states and S factor, and then we'll look at 10 to the 12th states per square centimeter per EV, like this. So the S factor is 0.9, I mean, 0.9 or so. So then the DIT, sorry, in that case, if you are a designer of electric transistor circuits, you don't control the device potential freely, independent of interface states. Then you will demand S factor of 1. I mean the 10 to the 11th density of states or so. But it is ideal anyway. So 10 to the 12 states per square centimeter, that is 0.1 of surface atom density, because the amount of silicon atoms on the surface is 10 to the 15th states per square centimeter for one more layer. Okay. So 10 to the 12th is 0.1%. So, okay. So if you want to make a rough device at 10 to the 12, DIT is okay. It is allowable. But if you want to make a precision device, you have to achieve S factor of near 1 or so. It means 10 to the 11th density of states. So let's look at the left hand side image. This is it is called super clean silicon surface. It is called silicon 111. The reconstruction is 7x7 size. And we surface scientists call this very clean, ultra clean surface. But please look at this. There are many defects, observates, vacancies, etc. The density is 10 to the 4th. 10 to the 14th, sorry, 14th, unbelievable. This is not actually ideal. This is a very dirty surface. So this is not an idea. This is not the ideal one anyway. So we have to make a more perfect surface to make devices. So scientifically controllable anyway, DIT lower than 10 to the 11th atoms is not required. Also, transistors technology node is basically does not relate to the critical values of DIT control. Okay. So this is an example of the controlling a DIT. This is my work, and this is my work. You can change. I can change the DITs like this for using a diluted HF. There are many only for cleaning of silicon surface, silicon carbide surface. There are many density of interface states. But if you etch the silicon carbide surface to make a cleaner surface, the density of DIT is reduced to 1 order of magnitude lower. And we invented a new technology to boiling water cleaning for silicon carbide before. So by using a boiling water, the density of interfaces goes down to 10 to the 10th, a very ideal one. So we can change the DIT engineering. So let's go to another story. So we have to understand the requirement of cleanliness anyway. So please look at this unbelievable images. So this is a experiment of residual sodium on silicon wafer by touching by gloves. Please note that the glove is a very new commercial one, but the very new clean one, it is just taken out and touch the wafer using the glove. This is not a dirty one, but a very clean one. But you can see the very large amount of sodium, 10 to the 13th nitrogen sodium atoms per square centimeter. Unbelievable. And also, let's go to the details of the contaminants. The first one is, as I told you, sodium. The second one is boron, phosphorus. The related material is HF, hydrofluoric acid. And the third one is ammonia. And the fourth is DOP or organic materials and heavy metals and H2O too. So I will explain one by one from now on. So this is a sodium story. There were very famous paper in 1965, Dion globes. And okay, I'll explain this one. So this is CV curve, capacitor curve, and voltage curve. So sodium can move in the oxide between metal and silicon. So then if you change the voltage, the sodium moves. This is the experiment. So first, the first one, original curve is the number of 1, like this. And they applied -10 voltage to the metal for 5 minutes. And the result is curve number 2. This no change from the curve number 1. But after that, they applied +10 voltage for 5 minutes. So the curve suddenly goes down to the minus voltage. Unbelievable that the difference was 30 voltage also, 30 volts also. So this is because the sodium goes down to silicon side from the metal side, because they applied the +10 voltage to the metal. And after that, they make electrical short for 15 minutes. Then the charge is reset, and the curve goes back to the original curve as a number 4. So this is a very interesting and a very unbelievable, wonderful experiment. So after that, we had an important common sense of semiconductor. Do not touch the wafer by hand. Your hand has a sodium, of course. And then let's go to the second one. This is not well known, but very important. This is a story of boron and phosphorus. So this is a DRAM's experiment. It has been done in Toshiba Electric in Japan before. And the horizontal line means a retention time, or retention time is a kind of a leakage current. It's the basic parameter of DRAM, because DRAM, the main function of the memory is retention time. The longer time for the memory charge is important in the memory, of course. So for the main, this guy measured many memory cells, totally 1 million cells in terms of leakage currents. So the main cells have a very long retention time, over 1 second, seconds, like 5 seconds or so. But maybe, as you know, DRAM is refreshing in the order of milliseconds. Why? You can keep the charge in a DRAM for 1 second or so. But in a computer, refreshing is the period is 1 millisecond or so. This is because there are very few bad cells in a huge DRAM, and we have to obey to the very worst DRAM. So the retention time is decreased. So please look at this one, and the for main cells, main distribution is like this. It takes over 1 second of retention time. But for the tails is the trend of tails is suddenly changed, and for 10 to the -6 rate, I mean that 1 cells in 1 million cells has the very bad retention time of 100 milliseconds or so. Unbelievable. And important thing is that this tail distribution is changing by changing the doping concentration of boron in a cell. This means that boron is diffusing, and very few boron atoms is diffused straight to the interface of leakage, and it makes a very bad phenomena of leakage. So anyway, this is well known, not well known, but professionals knows about this kind of phenomena. And another important thing is that HEPA filter or OPA filter has a boron or phosphorus in a glass wall to soften the glass. The glass wall is has the many boron or phosphorus in a HEPA filter or OPA filter. And also in a semiconductor fab, people use the HF. So HF dissolves from the liquid, and HF goes to the HEPA filter, and they melt a little by little the glass wall, and the HEPA filter emit the boron and the phosphorus day by day. So it degrades the DRAM specification every day, depending on the temperature and humidity. So this is a yield changing basic phenomena. So we have to prevent this kind of phenomena. So to do that, nowadays in a fab, people use a chemical filter to get rid of boron and phosphorus. And third one is aluminum. Aluminum, not ammonia. So people often uses chemically amplified resist nowadays. So this kind of complicated chemical amplified resist is very weak for the ammonia or amine groups, etc. So, so if you have a very small amount of ammonia species in your air, the lithography will failed by the ammonia. So like this. So yield of lithography is decreased below 1 ppb of ammonia. This is a well-known one. So let's go to the carbon or organic contaminants. People don't know about the reality of the carbon, but carbon have no deep level in a silicon band gap, so no problem basically. But we can make an acceleration experiment so to degrade the device. So this is the experiment. So look at the horizontal line means a breakdown field of MOSFET, okay, or MOS structure. So the unit is megavolt per centimeter or so. And doped DOP, like an organic material, is 10 to the 13th to 10 to the 15th. 10 to the 15th is the amount of the silicon surface density. So anyway, this is larger values. So carbon has no problem compared with heavy metal, etc. So, and also I will explain the DOP itself. This is a kind of a very famous experiment. So DOP is like a very large structure, and it's a kind of plasticizer. And DOP is a dioxyl dioxyl phosphate. I don't know the real pronunciation, sorry. So, and in a clean room, at the initial stage of exposing the wafer to the unbelievable dirty air, monoglyceride or DBP is observed, but it is decreasing, and the height of monoglyceride is changing to the diglyceride and triglyceride, and finally, all things is replaced to the DOP because DOP has a very planar structure and a very heavy molecule, and the Van force is stronger than other oily ones. So since DOP, the density of DOP in the air is very small, but the force to stick to the wafer of DOP is very strong, and the DOP is removes or take out other molecules, and the DOP makes a stick surface, and after 2 weeks or so, you know that the silicon wafer is covered by DOP only. This is very famous, interesting things. So anyway, but this is no problem because DOP is cleaned by Piranha solution. So we can clean the DOP. So that's why no problem. So this is a summary of the contaminants. So surface analysis like OJ, XPS, etc., has only two wide range, not wide range, small range, but the range is 100% to 1% or so, 2 order of magnitude. But for TXRF or ICP mass, etc., has a longer range, as you know. But it's not for devices, but for pure wafer. And also for electrical measurements, like a CV. Sorry, it's a noisy one. Sorry, it takes 30 seconds or so to announce it. But I will continue very slowly. Anyway, for 10 to the 11th, electrical measurement CV makes a very ideal CV curves like this. But the DIT is goes up to 10 to the 12th or so, and the CV curve is degraded like this. So that's not good. And so for transistor, that's why, therefore, 10 to the 11th is needed. So as a result, sodium, boron, phosphorus, heavy metals should be lower than 10 to the 11th atoms per square centimeter or so. This is a basic story. And another important advanced interesting thing is that non-H2 annealed transistor is distributed like this from 10 to the 13th or 14th. People in the world do not have the solution to decrease the non-annealed, non-hydrogen annealed transistors with the ideal electrical characteristics so far. So people have to solve the problem. Anyway, in other words, people have to hydrogen anneal the transistor or Pentium or your A16 in iPhone. So people have to anneal all of ICs in a hydrogen atmosphere to decrease the DIT. It's a kind of unbelievable one. So this is an advanced problem. I don't care about. I don't explain the detail so far today. And this is the whole basic story, but there are specific another problem, and I will explain it. This is a high resolution image sensor like this. So this sensor needs 10 to the 6 if you want to make most advanced image sensor. So unbelievable. But the device makers of image sensor don't know the reason why they need this kind of 10 to the 6. Unbelievable. So I mean that image sensor people ask scientists to make high resolution tools, and they asked process tool makers to clean all of things because image sensor is kind of a contaminant sensor. It is visible. So, and the yield of image sensor should be 100%. Otherwise, you will see the dot defects, etc. People don't buy this kind of unbelievable defective image sensor. So they have to make complete perfect sensors. So, and then this is visible. So they want to clean all of things, but they don't know the relation between the unknown item and the electric characteristics of the image sensor. The people don't know that. So no published papers. Anyway, sensor 6 is the most advanced one. And for commercial, so-so image sensor needs 10 to the 8th or 10 to the 9th level also. So this is anyway special case. Mainstream of the devices in the semiconductor needs 10 to the 11th is a basic number. And also, this is our original trial, but we have not published it. It's very interesting things, and I will skip it. So, and using a minimal fab, I will explain the minimal fab experiments. So, these things can be excluded for using minimal fab, but for particles generated by rubbing between materials, and we exclude this by designing to exclude rubbing motion, of course. And the resultant important thing for minimal fab is just to making a deep levels by heavy metals. It's kind of an internal contamination. So before, we don't care about this. So we meet a very unhappy contaminated factory. So I will explain it a little bit. So before, we have made this kind of very nice CV curves, and the resultant charges is 10 to the 10th, and the DIT's number is also 10 to the 10th, so very good. So you will see this kind of things. Minimum has a very good cleanliness, but by elapsing times of using a minimum fab, contamination degree goes up suddenly from 12, 18 or so. Unbelievable. We met a very unhappy thing. So we don't know why. I don't know why. So we clean minimum fab thoroughly. Unbelievable. We clean tools, unbelievable. So we did overhaul completely, and we recovered the minimum fabs. So internal contamination is very important, and we have to clean up, and we have to get rid of the internal contaminations. So, and the reason why we met the rapid increase of the DIT is that we met at the same time the degradation of the process itself, not the contamination. So as you know here, this is transistor aluminum. So aluminum is kind of a rocks. So there are many spaces, very small spaces. The contaminant gases can invade to the interface of the MOS structure. So the accumulated contaminants attacks by go through the porous aluminum gate. So that's why the reason of the rapid increase of the DIT and the density of charges, fixed charges. So, and also lastly, I will explain the minimal fab TXRF tool. It is developing. So this is the minimal fab TXRF tester. Since this is very small, so we don't use the monochrometer by the devising from the Professor Kawai. And this is kind of a basic principle of this TXRF. Important thing is that the glancing angle is wide, not narrower one, the very wide, larger one than you thought. So because if you take this kind of a larger glancing angle, the X-ray is incoming goes down to the crystal deeper, and so then we can measure the distribution of the materials for around say 100 nanometer or so. So then we can use the TXRF as a thickness monitor, not a particle detection, contaminant detection system. Yeah, we can do that anyway. So the detection limit, according to the Professor Kawai, is 10 to the 11th or so. Oh, this is satisfactory for us, okay, as I told you. So the SN ratio for our system has a 3.5 order of magnitude, like this, from silicon peak to the background. And the resolution is lower than 0.1 kb, like this, very precise one. So for us, this is satisfactory, okay. So this is tentative, temporary results, but we will anyway improving this kind of things for the application of thickness monitor and contamination control. Our detection limit is 10 to the 11th or so. It's okay. So let's go to the summary of part 2. Particles generated by rubbing and are important, while airborne particles are not important. For most all devices, 10 to the 11th contaminants per square centimeter is enough. For the most advanced image sensor, 10 to the 6th contaminants is demanded, but no reason. For the contamination level, TXRF is useful, especially in in-situ monitoring on contaminations or thickness monitoring. Using TXRF will become a strong tool. Minimum power is a brand new system to protect the wafer space for contaminants from outside. As for internal contamination, minimum power should be cleaned or overhauled occasionally before severe accumulation of contaminants. That's all about my presentation. Thank you for your attention.
So thank you very much for a very interesting talk about the contamination, or especially we are interested in the contamination species and its concentration. So could you give us the some order of the magnitude? So it is 10 to the 11th or something, but for the mega fab, if we compare with the mega fab and the minimal fab, so its circuit width. How about the circuit width for minimal fab? It is
okay. Good question. As I told you, the 10 to the 11th is determined by the DIT is a kind of a basic mechanism, physical mechanism of silicon interface state mechanism. So it does not depend on the design rule itself, no relation. So for wider, big transistor and a small transistor, the 11s are the same for both. No relation, but people don't understand this. People misunderstanding it. No.
So that means if the minimal fab, could you give us the typical width of a circuit?
That's fine. Our width is 1 micron to 10 microns. But as I told you, the mechanism, the determining mechanism, the number of the contaminants for atoms is determined by the physical reason of Schottky body height or most structures of DITs. Yes. So it does not depend on the fabrication design rule.
Are there any questions? So I have a comment that the TXRF is invented by Yoneda and Horiuchi, not by me.
Really sorry. So anyway, you are advising me. Thank you very much. Anyway,
Can I have a question?
Yes, please.
How to get to the reference sample or standard sample or 10th, 11?
No, we don't use a standardized wafer of contaminants. We only use this wafer for various targets. So we only observe our daily used wafers. No, we don't use standardized contaminants of the wafer. No.
Can I have the cross check or other method of the ICP mass or?
Yeah, we did it. We use this ICP mass, of course. Yeah, it is reasonable. We had a reasonable result. No discrepancy.
The destructive method and in this reactive method, cross-check the very difficult.
Sure. But this is because that you don't control the contamination in your space. So that's why a wafer becomes dirtier if you elapse the time. So, and if you move the wafer, the wafer is degraded or contaminated. That's why. That's why it is difficult. So in a minimal fab, the contamination is controlled because contamination is get rid of. It is removed from inside the minimal fab. So this kind of things is very easy to do that. That's why I believe that you don't listen this kind of summary of the contaminants. But for us, this kind of things are very easy to do that if you use a minimal fab. That's why I can say that a very clear image of the contaminants and problems.
And one more.
Yeah.
I saw now you indicated on silicon where fingerprint sodium imaging. How to get the imaging? So
this is not my work. This is other people's do that using a mobility charge monitor.
How to?
It's kind of a CV system anyway.
How to get the image?
Oh, this is not non-contact CV system like the Kelvin probe. So you can measure the charges, local charges, by using a very small a condenser. So if you have a sodium, the charge amount is different in a local place. So the charge is changing. Okay.
Okay. Not SEM-EDX.
Not SEM-EDX. This is a local, very small local probing method. Like it.
Other questions? Yes, Ursula.
Yeah, thank you so much for the very interesting talk. Maybe just a tiny question. So the inline TXRF, is that supposed to work in vacuum, or is that just so what is the surrounding atmosphere?
Are you talking about the basic specification of minimal fab itself, or specific experiments? Which one? Is this one?
I was thinking, so that was maybe I have misunderstood that you're planning to integrate a TXRF system in the minimal fab. Yes.
Okay. As you know, TXRF work in vacuum or in air, of course. So in our TXRF system, we evacuate the atmosphere, the air. So it's a kind of a vacuum system.
Okay. Yeah. Thank you.
You're welcome.
Okay. Other questions? I have one question. So it's a non-monochromatic X-ray irradiation. That means X-ray diffraction from
that's right.
silicon wafer.
Yeah. This is a diffracted
interfering. Okay.
Yeah. So if we use a quartz wafer, it's not the crystal. So we don't see the diffraction peaks. It is smoother. So it depends.
Okay, it's a shortcoming of the non-monochromatic TXRF. So if you can use monochromatic TXRF, maybe this kind of peak can be eliminated.
Sure. But in that case, we have to shrink the very monochromatic unit to this size. Oh, I believe it is impossible. But if you can do that, I want to introduce a monochrometer. But anyway, the two sides like this. So we have to insert the monochrometer if you want. So that's a difficult work, I believe.
Okay, other questions? So if not, I'd like to close today's session. So thank you very much.
You're welcome. Thank you very much for your discussion. Thank you very much.
Thank you.
Welcome.
Thank you.
Thank you for the presentation.
So Ursula, some announcement of the next journal club.
Yes, maybe announcement for the next journal club. That will be on the 27th of October and will be given by Dr. Dieter Ingerle from the Atomic Institute at the TU Vienna. And the time is not fixed yet. The topic will be on grazing incidence XRF, but more details will come soon.
Okay, thank you. So see you next month.
See you.
Bye.
See you.
Bye.
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 Bye. Thank you.
Bye-bye.
Goodbye.
See you.
Thank you, Yasna.
Hello.
Bye.
Finally. I'm sorry, but I had exams this morning, so I couldn't be present at the beginning. In
Don't worry. Bye.
Bye.
Bye, Ramon.
Bye.
Bye, Ramon.
Yeah, it's
Bye-bye.
amazing that you always have time.
Nandura.
Hi.